Hi, we are going to work through 812 together. We're going to kind of pick and choose the problems that we look at. So let's go ahead and get started. Looking back at what you did in our first investigation for this chapter, can you think about the answers to the following questions? So what is the maximum number of roots a polynomial of degree 3 can have? Now before we do that, two quick definitions, right? Because you got to know what it means to have degree 3. So degree is just your highest power that you see in your expression. All right, so if we see an x cubed, then our highest power is 3, our degree is 3. The other thing that's important for us to make sure we remember, and I think most of us know this, is what roots are. Those are just your x-intercepts. So if we think about the number of roots a polynomial of degree 3 can have, then hopefully we remember seeing stuff like maybe this, or maybe even this. And those could possibly be ones that have degree of 3. And if we look at the number of roots that we see here, this one has 3 roots, and this one has 1 root. So the maximum number of roots would be 3. So then carrying that through, what do you think the maximum number of roots of degree n could be? Well, hopefully that would also turn out to be n. And then clearly, can a polynomial of degree n have fewer than n roots? Well, if we look back up at the problem we just did, we can see that we have a degree of 3, and we can have one that has 1 root. So yes, absolutely. Okay, so let's look at this next problem. We're going to kind of talk about one of these together, and then I'm going to have you do the same thing on your own. And actually, I'm going to talk about 3 different things here because I want us to start seeing the relationships that are taking place. So the first thing I want us to look at is what's the maximum number of roots there could be? Okay, that's our first question. The second question is then, what's the minimum degree? And then the third question is going to be, what is our the number of turns that you're seeing? Okay, so 3 things: maximum number of roots, minimum degree, and number of turns. So in order to figure any of those things out, we're going to put an imaginary x-axis somewhere that would give us the most x-intercepts. Okay, so then if I do that, that would be something that looks like this. Okay, so this is my imaginary x-axis. If I look at it now, if my maximum number of roots is going to be the number of times it touches the x-axis, well, in this case, that's 3. Well, we just looked above at how the maximum number of roots is going to impact the minimum degree. So our minimum degree is going to be the same as the maximum number of roots. And now this last thing is a little interesting. It's the minimum number, or not minimum, it's the number of times the graph turns. And by turns, what I mean is, think of it as a roller coaster and you're going up, 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 and then all of a sudden you start going down. So this is a turn right here, okay? And then think of this as, again, going down, 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 and then turning and starting to go back up. That is a turn. So what we actually have, is 2 turns on this graph. Okay, let's do one more together, and then I'll have you try this on your own. So once again, I'm going to draw in an x-axis at some place where I see I'm going to get the most number of intercepts. So there's my x-axis. Number of roots is how many times it touches the x-axis. So this is the maximum number of roots, and I get 2 this time, which we know that impacts our minimum degree. So our minimum degree will be the same as the maximum number of roots. And then finally, the number of turns. Okay, so the number of turns is how many places where it starts by going up and then turns and goes down. So we just have this one place where it turns this time. Okay, what I want you to do is pause the video and try the next 2 on your own and come back and check your answers. Okay, so compare what we have. Hopefully we have the same information. So notice that in all of these, you are hopefully seeing a pattern happen, right? Because the maximum number of roots and the minimum degree are the same in each of these. But notice what the relationship is between then and the number of turns. Okay, so the number of turns is always one less than our max roots or minimum degree. And that's an important thing that'll come back a little bit later. So if you want to make a note of that, you can. We're going to talk a little bit about this idea of, positive and negative, like orientation of the graph. And that comes from looking at the right side of the graph. In other words, it asks which of the graphs above show that as the x values get very large, the y values continue to get larger. In other words, as we look at the x values getting more and more and more positive, going out towards infinity, we look at the right side of the graph, okay? As we look at the right side of the graph, what is happening to our y values? So as I continue to travel along the right side of the graph, look at my y values in each of these graphs. Okay, so the extreme right side of the graph. And what I'm noticing is that on the right side of the graph, the y values are getting larger in A and C, but are getting smaller for B and D. And we call that increasing and decreasing. I'm not sure why this ended up on this page. Let's talk about this idea of positive and negative orientation. So positive orientation are those graphs that have a right side that points up. So that would be graphs like A and C have positive orientation. And then therefore negative orientation would be graphs like B and D. That just means the right side either points up or down, depending on if it's positive or negative. Okay, I'd like you to pause the video here and try problem 829. Use Desmos if you need to. Make sketches, try to answer these questions as best as you can, and then come back and check your answers. So take a quick minute, check over what you've got. You should have for this part A, how are they similar? They have the same number of roots, same number of turns, and they both have a positive orientation. Whereas the y equals x minus 1 to the fourth, which is the blue graph, is actually a little bit flatter. They also have the same y-intercept. I didn't write that down, but that's something to think about as well. Could the equation from graph B from the previous problem have a degree of 4? Sure. Remember, we said that that's a minimum degree, not a maximum. And then for part C, could it have a degree of 5? No, because then the maximum number of roots would be 5, and then the number of turns would be 4. And if you look at that graph, there's no way to make that happen. So then how are x cubed and x to the fifth similar or different from each other? They both have an odd power, and they could have the same number of roots. In the investigation that you did in the previous lesson, you probably came across, or you didn't probably, I know you came across problems like this, where you have this x minus 5 or x plus 5 squared being a factor of your polynomial. But what's interesting about that is that it's a squared factor. What we see is that it produces a double root. In other words, if I were to solve x plus 5 squared as a factor to figure out what my roots are, I would have to set it equal to 0. I'm actually going to get, I know it seems weird, but I'm going to get x minus 5, but it's going to show up twice because I could solve it this way, or, guys, I could solve it like this. I could take that x plus 5 and write it as x plus 5 times x plus 5. And then we know that we set each factor equal to 0 to find the roots. And what's ending up happening here is we're getting the same root twice. So we call that a double root. But on the graph itself, what we see happening is something like this. So here at x equals negative 5, I don't know what the rest of the graph looks like, and I don't care. But what we see happening is something like this. The graph itself, and we'll just kind of do this, the graph itself bounces off of x equals -5. So what we see happening with a double root is this idea of a bounce, where the graph itself bounces off the x-axis and keeps moving up. And if you zoom in even closer, what it almost looks like in this little section right here is a parabola. And that's why we call that a double root. It has an exponent of 2, it bounces off, it looks like a parabola, because anything with this power of 2 is a parabola, right? Well, now we've got this power of 2 sort of hidden within the rest of the polynomial. So we have this behavior that looks like a parabola within the larger picture. That's what you get when you have a double root. Now, I'm not going to actually have us go back and look at the equations themselves, but the idea of a triple root. So if a double root has a power of 2, then a triple root might have a power of, let's say, 3. So let's say x minus 1 cubed. The same kind of thing is going to happen here. If I were to look at just the graph at x minus 1 cubed, here's, we'd have a root of x minus 1. Look, we do this, right? We have 3 different equations that we would set up that just so happen to all give us the same root. And that's why it's called a triple root. But if we have this root at x equals 1, and I graph my function here, so my graph could look, something like, blah, 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 all kinds of stuff happening there. Let me try that again. And it looks something like this, right? This is a bigger picture. I'm not sure what the rest of the equation looks like. I'm just talking about a specific root that is a triple root. Now, if I zoom in on that, so we just look at the behavior that's happening around the root, this sort of looks like a cubic graph. It has that behavior where we call it a slide. It slowly kind of levels off a little bit, and then it continues moving in the same direction. So it still goes through the x-axis. It just slides through the x-axis. So we're going to call that a slide. Okay, I'm going to talk through this, but you have it all written out for you as well. What we're going to look at are number lines that can represent a polynomial graph. And what we'll see is that anywhere that there's a bold part to our number line, that represents any outputs that are positive. Anywhere we see an open circle, that's going to represent intercepts or roots of the function. And then when there's no shading, that's telling us our output is negative. So what I want to do is sketch a possible graph for each of these number lines. Okay, so we'll need an x-axis and a y-axis here. Okay, so important pieces to understand here. Anywhere we see these open circles, 1, 2, 3 open circles, those are going to represent roots of our function. So the first thing I'm going to do is I'm going to put those on my number line, or on my graph. So -3, -1, and 4. Those are going to be roots. So let me identify those with x-intercepts on my graph. Anything that's above the x-axis is going to be shaded on our number line with green. So if we look at this section of the graph and this section of the graph, those are both shaded, which means that everything between -3 and -1 will have a positive output on our function. So that's going to have something that looks like this and then like this. And then there's no other roots, so I know that it keeps going to the right. Anywhere that it's not shaded, so that would be these parts of my graph, that's going to represent negative portions of my function, meaning anything below the y-axis. So anything to the left of -3 and anything between -1 and 4 will be negative. So now I've got a quick sketch of my graph. Go ahead and try the other 3. Okay, so check what you have with what I have. Notice a couple of these have spots where between 3 different intercepts it stays positive. So that means it's got a bounce in there, okay? So now we want to compare the idea of an even degree versus an odd degree. So remember, that just means it has a highest power that's even or a highest power that's odd. So hopefully what you're noticing is that even degreed polynomials, both sides of the graph will point in the same direction. Whereas in the same direction. So meaning both sides, both ends of the graph either point up or down. So what's happening in the middle is irrelevant, right? The graph could be going absolutely insane in the middle, but as long as the ends are pointing up or down, it's even. Now, with odd graphs, you have that the ends point in opposite directions, meaning we'll have one side pointing up and one side pointing down. So you might have a graph, that looks like one side, right side points up, or left side points up, right side points down, or maybe left side points down, right side points up. And again, it doesn't matter what's happening in between here, okay, as long as we have the ends pointing in opposite directions. So pick a couple of graphs that you did in your investigation from the previous lesson and draw your number line for it. I'm not going to give you an opportunity to check that because everybody could pick something different, so just use what we did above to kind of guide your work. Okay, the last thing we're going to do today is look at how we could sketch the graph without actually using any graphing technology. So we need to identify our roots to start, and that's what I'll do by looking at my equation. Now, hopefully you saw this in your investigation, but these factors help you identify your roots, and you should know that even without the investigation. Our roots are going to be, for example, the factor of x minus 4 gives us a root of 4, because when we set x minus 4 equal to 0, we get 4. So my roots are going to be 4, -2, and +1. Now I'm going to go ahead and put those on my graph. So -2, 1, and 4 are my roots. Now I'm going to figure out what my degree is, because that'll help me determine what the ends of my graph are going to do. So the degree is looking at what the highest power would be. Now this is written in factored form, so we would have to actually think about what would happen if we multiplied this all out. So take, your x squared here would result in an x squared as your highest power. We're going to multiply that by another x and then by another x. So our degree is actually 4. Now what that tells us is that we would have a maximum number of roots of 4. But what we're seeing is only 3 roots, and that's because when you look at x minus 1 squared, it's actually going to have a bounce, right? There's going to be a bounce right here. So when I'm looking at my graph at x equals 1, I know that that will have to be a bounce on my graph, right? So degree of 4, there's a bounce there at 1. And then my ends of my graph, we call that our end behavior. So the end behavior of the graph, it's all based on, whether it's an even or an odd degree. So this is an even degree, and this is what we just talked about a moment ago. It means either both ends are going to point up or both ends are going to point down. Now, the key to that is whether it's a positive or negative in front of your graph. Well, since the whole thing is positive, imagine if we had a negative x squared. We know that flips it. But a positive x squared is going to point up. So we know that both ends of this graph are going to point up. Okay, so that helps us get sort of a start, right? If we know that this end of the graph has to point up because this end of the graph points up, then we know we start out coming down like this. We're going to go through the graph, Then we're going to kind of turn and come back up here. Now we don't go through, we bounce, so that means we come back down, and then we turn and go back through that root and point up again. So this is just a sketch, right? I'm not worried about, you know, these valleys or how low they actually go. So if you just get a sketch, that's fine. All right, pause the video, see if you can graph the other two, and come back and check your work. All right, so you should have something that looks like this. What I want you to kind of watch for, and maybe it'll make it a little bit easier, but the end behavior piece of this goes back to our positive or negative orientation. If the whole graph is negative, like you see here in A, then it has a negative orientation, which means the right side of the graph points down. And then what we know, since this has a degree of 3, is that the ends are going to point in opposite directions. So I know if the right side points down, then the left side has to point up. So then when we look at C, we can see that because this has a, you know, there's no negative out in front of this, we know it has a positive orientation, which means the right side points up. And then once we figure out the degree is an even degree, we know that the two sides have to point in the same direction. So these are things that can help us come up with our graphs. Also notice in C there is a slide right here at -2. So you want to kind of try to graph that as best you can. Okay, go ahead and check Classroom for your assignment that'll go along with this, and then watch the other lesson when you're finished.